Jabber scribe. Someone signed into Jabber already. You willing to do it, Aaron? Okay, Aaron Falk's going to scribe for Jabber. Matt Ford is doing the note-taking for our minutes.
You can start. Just on time.
And we're going to start on time because we have a tight schedule today. So good morning, everyone. I'm Dave Plonka. This is Mirya Kulevin. We're the co-chairs of the Measurement and Analysis for Protocols Research Group. The group, well, let's start off with the note well, the new note well slide. The note well is about in the IRTF, we use the same intellectual property rules as the IETF. So instead of just saying you should have seen this before, it means that if you're going to share information here, that it's governed by the rules in these RFCs. So look at that if you get a chance, or if you're going to share things in an IRTF or IETF meeting. Administrivia, the charter for our group is up here. I'll give you a short overview of what the charter is about. Measurement Analysis for Protocols Research Group is meant to be, well, literally that measurement analysis, but to serve the protocols and the operation of those protocols in the IETF. So we're trying to bring the research community, of which some of you are, and the IETF community, of which some of you are as well, together to show you what some of the latest measurement data about real protocols, and hopefully solve some of the either design problems, new architectural ideas, and potentially deal with performance issues that we observe operationally. We have a mailing list, of course, and the links are here. The slides are up for today. All the slides for each of the presentations are linked, and we can join remotely via these audio and MeetEcho links, and the Jabber link is there as well. So the agenda for today is we've got 2.5 hours. It's almost completely full. So we'll start off with, once we go through here, 2 project advertisements. We invite you, if you have a project that's related to this, but we don't have either content enough or time enough in the meeting to present it, we'll plug it by an advertisement there. Then Michael Abramson will come and talk to us for 5 to 10 minutes about identifying IPv6 reluctant devices and hosts. And then we'll move on to fingerprint-based detection of DNS hijacks using write batlist by Pavel Foremsky. And then a presentation by Pablo Alvarez about his experience with rate limiting of ICMP error messages in v6 trace routes. So basically, an example of something operationally that's different between v4 and v6 and what we can do to mitigate that. Then I'm going to present, not in a chair role, but some recent measurement work that I've been doing in a way to hopefully improve the way IPv6 address anonymization works. Again, something that's different than the way that it might have worked in before. And then we'll move on to Toki talking about measuring latency variation in the internet, how deep are queues in bottleneck routers and such. And then we'll move on to measuring YouTube over IPv6 with Vibav. And lastly, Jana from Google, we've invited him to come and present some soon to be published work about internet scale deployment of QUIC. So we've got 4 things that are v6 topics, which is one of the directions that I want to go, but that's our agenda overall. And then Mirya suggested, or we wanted to share with you a little bit of how we did the agenda this time. The group is meaning to be reporting on nascent measurement results that would help IETF efforts, but we're also trying to do some proactive things and seeing if we can call you guys to help out. So there's one item this time that's not a report of measurements. It's basically a call to arms or call to help, and that's the first presentation. We didn't solicit for presentations this time because there was so much interest and people sent them to us unsolicited. So if you have thoughts about that, share them on the list, share them with us, or if we have time at the end, you can comment in front of the audience here. But right now, this is an example of one that I guess Mirya and I curated the agenda this time. So let us know if that works for you, if you think we're doing a good job or a bad job here or offline. So let's move on to the 2 project advertisements. The first of this was from Matthias Wallisch, and he's got at this URL, he's got an electronic preprint of a nice paper about measuring our PKI infrastructure and determining, basically this is a technology developed in the IETF and measuring whether or not and how it's being used and not. And 2 key observations they had is that the existing methodology from the literature which was meaning to determine completely passively whether the PKI was being used to filter, They found some problems with that and improved upon it by introducing an active component to detect it, and detected a number of ASNs that are indeed using the RPKI to do this kind of route validation. So if you follow the link to the paper, those authors' contact information is in there. And then the second ad is from Stephen Strohs, who's with RIPE, and Stephen is in the blue shirt, RIPE shirt here in the front. What he wants to tell us is that RIPE is batching up daily aggregations of their measurements. So for measurement researchers, you can just go and pluck this stuff and much more conveniently get access to it and use it. So if you have questions about that, find Stephen or write to him at his address at the bottom of the slide there. Mirya, anything else you want to share now? The blue sheets, we're going to circulate those. 2 of them. Looks like we've got quite a few people again. So please sign the blue sheets.
Oh, thank you.
So I'll get the slides up and you can take.
Hello.
Yeah.
So I didn't send you a slide, but while you're setting up, so we had this ANRW workshop on Saturday for the second time, and we are planning currently. So I'm Lars Eggert, I'm part of the steering committee of that workshop. So we're currently planning to have it next summer in what we thought was San Francisco, and it's now Montreal. So there'll be a call for papers and stuff. So ANRW has it's trying to attract applied work, and a lot of the applied work has a lot of measurement in it. This year, we unfortunately were not really that aware that we badly conflicted with the IMC deadlines. We're trying to avoid that next year. But keep that in the back of your mind if you have something that you think is applied, such that, maybe it's struggling a little bit at a very scientifically oriented venue. The ANRW specifically wants to sort of bridge this gap between practitioners and academics. If you are like a North American academic that is doing good work and would like to be considered for PC chair, let us know. We're looking.
Lars, can I ask you, so where do you want us to send comments and questions or ideas about ANRW? I
think IRTF Discuss would be the home for it. The workshop doesn't have its own list. And under the SIG, I don't think we have something set up. So I think the IETF Discuss, I'm volunteering and sitting next to Alison and she's not hitting me yet, would probably be a good place to discuss that.
All right.
Thank you.
So we start with our first talk, or like presentation or call for help. Go ahead, Mike.
Thank you. Hello, my name is Michael Abrams and I work for Deutsche Telekom. So I've been involved in IPv6 enablement there and at other places for quite a long time. I've been interacting with a lot of other operators who are doing the same, and why they do it and so on is we've identified a potential future problem that we would like to measure. And we try to come up with a name for this, and this is why doesn't something use IPv6 if it's available? So if the ISP has done its homework and it's now IPv6 enabled, the home or whatever, and there is now not, the devices there are not using the IPv6 connectivity, instead of running its traffic over IPv4. So there are a few reasons. Content is not available over IPv6. This is a given. That can be, probably is going to be fixed over time. So that's not the immediate concern. The larger concern is that the device or operating system is not IPv6 capable, because this is something that might not get fixed. It might reside on a device where the device and the operating system supports IPv6, but the application is using APIs that don't support IPv6. Or actually the content is referenced using IPv4 literals, could be hard-coded in the application, or that's what's sent to it. The last one can probably be fixed, but if it's hard-coded and the application is not updated, then this is a problem. Operators want more of the traffic over IPv6 because running to both v4 and v6 at the same time increases complexity, and going forward there's going to be more carrier-grade NAT and so on, and these boxes are expensive both from a CapEx and an OpEx point of view. And the end goal that we all want to reach is to not have to support IPv4 at all and just have a single address family where everything just works. So there is a worry that both historically And going forward, there are new devices and applications and so on being put into the network that do not support IPv6. So my smart TV from 2012, perhaps that's like, okay, that's too old, it's never going to get updated, the operating system is abandoned, yeah, fine, that's never going to get IPv6. The problem is that there are still devices in 2020 being put into the network that does not support IPv6. That is a much bigger problem. Anyway, we would like to, so this is the concern, that even though the ISPs are now doing their part, application, what's an application vendor? Anyway,
Manufacturer.
Application manufacturer, device manufacturer is not doing their part here, and this is going to increase complexity and in the end potentially cause problems for, because there's a lot of concern with IPv4 quality going down because prefix hijacking, because of lack of addresses, and all this might cause a device that you just use IPv4 to have worse user experience than one that is using IPv6. So the ask to MAPRG, is that how you?
Yep.
MAPRG, okay. Is there a way to identify this? Is it possible to figure out if a device is sitting on dual stack connectivity, but it's not using it? And then can we fingerprint it? Can we figure out why? Can we measure this over time? Because I think a lot of ISPs would like to keep the IPv4 traffic at least in absolute terms not increasing. We would like to decrease, but at least if it doesn't increase, we don't have to do new investment in devices to support IPv4 in the network. So we would like to measure this over time, and also if we can identify which are these devices and applications, we can talk to their manufacturers and try to lobby them or whatever, try to convince them in order to enable IPv6 on these devices, applications, content networks, whatever. So that's the ask.
So Michael and I had this conversation, and at least on the behalf of the chairs, I said this is something we're interested in. I think this is a higher bar than we should set for ourselves. Instead of giving reports even of nascent measurement work, can we proactively do something someone else in the IETF comes to us with? So we have a few minutes to talk about it now. If people have ideas about observation points where we could see this, how we might collect it without doing finger pointing, but put it in a positive vein, I'd love to hear that. Fred?
So a question, Michael, and I got this the other day from NASA, a gentleman over there that operates, I think, G-Root or something like that. It was looking at IPv6 deployment and some of the issues in it, and one would be related. He was suggesting that we go for interoperability tests where we can prove that devices actually do work IPv6 only and publicize them so that people that are like your friends here might get the message in a positive manner. Would that kind of a thing be useful to you?
So there's been, I think this is like for home gateways that have the whole like IPv6 ready, but this would be for like applications or and devices, or?
And this would be for really any kind of device that one runs. I mean, Cisco is working with a number of its customers on IPv6 only deployment, and number of networks are working on it. I'm sure they're working with all their friends. So you're kind of extending this to the reach of the home or other places.
Yeah. So it would the whole thing that Apple did with you can run NAT 6.4. You can test that on your MacBook. Like if you connect a device, you can create a Wi-Fi that is IPv6 only. That's one way of testing this, I guess. So you could say to any manufacturer something like, how does this work? At least then you know that the device and the application can speak IPv6, and that would be, then if the content it becomes available over IPv6, it will still work. So if we could spread that approach into like more places, that could definitely be a one way.
Hi, Tim Winters from the UNH IOL. So we're heavily involved with the Ready Logo program that obviously covers, stacks on devices, right? There's 1,500 devices on that list that show that they have IPv6 stacks. Obviously, that doesn't cover things like, as you've noticed, there's not a smart TV on that list. So it does some coverage, but it doesn't cover everything. And the other thing that I've been hearing from people is a lot of times at testing, we can configure the device to turn on V6, but that doesn't mean it has it on by default, right? And for some people, that's a killer. I think that's something the program might look at changing in the future, saying that it's a requirement of getting the logo that you turn it on by default. I think that's something that this group wanted to see. That's something we could push inside that committee. But right now, the way it stands is basically they can configure it. From the testing we do at the university, we've seen a lot more application testing in the last year in V6 only environments. So we're getting a lot more vendors who build applications wanting to verify that. So we're starting to see a movement in this direction. There's no public list at the moment, but we are seeing vendors one-off come in and want to test those kinds of environments.
Yeah, I would love if the program required IPv6 to be default on, so that the user didn't have to do anything in order to get this working. Because is there a reason why they don't want to do that? Yeah,
so there's a little bit of history here with this. In some cases it would cause users, maybe today this would be a different story, but at the time the feedback we got was that people don't always want it on all the time. I think that world has changed. I mean, we made that rule a while ago. I think we probably should revisit it. So I'll take that action item from today and come back and see what I can get the local committee to agree to.
That would be great, because I mean, I typically say when people are saying that the market isn't requiring IPv6, I usually say the market doesn't require IPv4 either. They typically want internet access. The service they want is not IPv6 or v4, it's internet. And today it's both. So in order to have proper harmonic connected internet support, you need both stacks, and it needs to be default on.
So this is a comment to the previous speaker. I actually have a brief talk this afternoon in V6 Ops that would be directly related to that. I talk about what I had to go through to turn on IPv6 in my home router, and you didn't want to go there.
All right, thanks, Fred. So I think we covered in the 10 minutes what Michael and I wanted to convey. It's an invitation to participate in this, or an invitation to share ideas about how we would go about this measurement study. And I guess the challenge I want to raise to the group is to say, by the next time we meet, which is likely in 4 months, can we report then, if we have something substantial, what it would be? And it's not really asking time of the research group, so it doesn't need an approval other than the idea is we'll broach it in the mailing list, and if we have something to share by then, we can. But with this community, we should be able to have something by then, at least a set of ideas or a roadmap for about how we might do such measurements and what value we can bring to the community by sharing it. So, thanks, Michael.
Yeah, thank you.
Okay, we go on with our second talk. Pablo? Over there. This is on fingerprint-based detection of DNS hijacking. And as many people do today, he also used the RIPE Atlas platform.
So good morning, everyone. My name is Paweł Foremski. I work for Farsight Security, and I'm a PhD student with the Polish Academy of Sciences. Today, I'm here to present you my work done with my colleague Maciej Andziński of NASK. The work was started during the recent RIPE NCC DNS measurement hackathon, and it's called fingerprint-based detection of DNS hijacks using RIPE Atlas. So I'm sure that most of you know what DNS hijacking is, but just as an introduction, a situation in which you think, for example, that Google 8888 is responding to your DNS queries, but in fact, someone in the middle is hijacking the queries and responding with different data, but it may also provide with the valid data, but some kind of surveillance is happening, and you don't know about this. And so what's the RIPE Atlas thing? It's a measurement platform consisting of 10,000 embedded Linux boxes distributed around the world. It's run by RIPE NCC, which provides a central API to start measurements like ping, trace routes, things like that, and collect the results back. So what was our research idea for this topic? Well, we thought about that we can select DNS queries from each of the probe to select target IP address of the resolver. And our hope here is that we would be able to spot differences in the replies if the server was hijacked. So we rewrite the replies that we collect at a single probe as feature vector. This is the fingerprinting stuff. And finally, we use machine learning to check if the fingerprint matches the model. That's the detection part. For this research, we focus on Google DNS and OpenDNS because these are the two biggest providers of public DNS resolver service. But the methodology is generic, so you can adapt it quite easily to other operators. And we wanted to know, first of all, how prevalent hijacking is in different perspectives, which are the most risky ASs, and finally, what does it all mean to the internet. Well, the features that we use, I mean the queries, were a bit limited by the Atlas API, which provides quite a restricted API. That's for purpose, that's for security of the volunteers who run the probes. That's good. So we weren't able actually to do some low-level bit flipping stuff, but we had access to DNS replies in wire format, and also the platform measures timing quite well, so that was useful. So we started with chaos TXT queries. These are kind of queries. This is a class of DNS queries that lets you to actually query for the state of the server rather than fetch some data from the DNS. We used the three most popular queries: hostname.bind, version.bind, ID server, which should give you things like the hostname of the server or the software version. But we also know that, for example, Google and OpenDNS don't answer these queries. So if we see a reply, that's a clear indicator that something bad is happening. For the second set of features, we checked things like DNSSEC support, like querying for dnssec-fail.org, which has invalid DNSSEC signatures for purpose. It should fail. We also queried for DNSKey for .pl, which shouldn't fail. I mean, if someone is not doing something bad, like stripping off all of the DNSSEC from the DNS. We also check for IPv6 support by querying for the fully qualified domain name that is resolvable only if the resolver has full v6 connectivity. We check TCP support. We check replies to non-existent domains. If we got a successful reply, we noted the IP address, ASN of the network, and finally we check the QNA letter case insensitivity. Finally, we also did some more network testing. I mean, not really DNS, strictly DNS related, like running ping requests and measuring the trace routes. And here we stored hop count, AS path length, and parameters of the exit AS, that is the exit just before Google or OpenDNS. Finally, we used two DNS whoami services. The first, the most famous, I would say, whoami.akamai.com. Whoami service is a DNS authoritative server that should reply with the IP address of the resolver, I mean the non-anycast public IP address. But because the first service is so popular, we also implemented the same service on our own domain. Hopefully that it's not well known and it's not filtered out, for example. Some people could argue that the last feature is enough to detect hijacking, but we actually found DNS resolvers in the wild that although they returned valid IP addresses that is belonging to Google or OpenDNS, they were hijacked. For example, they were returning IP addresses to non-existent domains. So this feature is not enough. All right, as to the measurements, we ran them not even a month ago at the end of June this year from 10,000 probes, from 3,000 ASs. And we burned some few million RIPE Atlas credits. Thanks to Vesna and Steven for that. And we published all of the tools and all of the data on GitHub. Everything of this project is open. You can use it, hack it, anything. And here are the links to spreadsheets, Google spreadsheets for the raw data for Google and OpenDNS. Just to give you a glimpse of the data we collected, here on the left-hand side you see the latency, the histogram of latency to Google resolvers. On the right-hand side you see the hop count. For OpenDNS, when we compare these two, the median latency is a bit higher, but the hop count is a bit less. I mean, the median is a bit less. All right, what about the ground truth? Ground truth is an information that is this fingerprint really a fingerprint of a legitimate server or not? There is no way to obtain this from network operators because usually when you do such stuff, you want to hide. And also the number of networks was so big that it would take us ages probably to contact every operator. So we had to make some assumptions. So we assumed that the most common fingerprint collected around the world is the legitimate one. So any deviations in some of the features, I mean the 7 most obvious features, like replying to non-existent domains, is a clear indication that the server was hijacked. And finally, we use a machine learning classifier that hopefully will learn how to use all of the features, that is more than 40 of them. However, we still work on a better ground truth method. Finally, machine learning classification. We compared 3 different machine learning algorithms. We evaluated 30 times each of them to get some good estimates of the performance. By starting with just K and N, with 3 neighbors, we had something like 80% of accuracy and about at least a few percent of false positives. So moving on through the decision trees to random forests consisting of 10 trees, we obtained 93% of accuracy with close to 0 false positives, still 6% of false negatives, which means that our method is more likely to miss a hijack than to label a good resolver with the hijack label. So finally, we classify the rest of the data using the random forest classifier, and again, implementation is on GitHub. All right, here are the results. On this map, the color encodes the number of RIPE Atlas probes that we believe that have the Google DNS resolver hijacked. As you can see, the Russia is on the top, but if we divide the number of probes with hijacked DNS by the number of probes within this country, we get such a map where the color encodes the probability of the DNS being hijacked. And the countries that are leading this are Madagascar, Iraq, Indonesia, and China. However, some countries have quite small number of RIPE Atlas probes still, so we filtered out the countries so that we left only those with more than 10 probes. Here, Indonesia and India and Russia are at the top. On the other side, Canada, Austria, and Norway are the countries with the most probes, and as far as I remember, 0 probes had their DNS resolvers hijacked. These are the results for OpenDNS. We found 94 probes with hijacked DNS. Again, converting them to probabilities are like the following, and again, filtering out countries with less than 10 probes gives us such a result. So again, Indonesia, India, and Iran have the most chances of DNS being hijacked. Switching the perspective to ASs rather than countries, it was very interesting that we found ASs with 80 to 100% of the probes having the DNS hijacked for Google. That was also the same for OpenDNS. Maybe the ASs were a bit different. However, we found that when we compared the probe IDs with the Google resolver hijack with the OpenDNS, we found that the most likely situation is which both of the resolvers will be hijacked. We found 68 probes with such features. So finally, we ask, what are the most risky ASs? Or put it differently, which are the kind of systematic hijackers? I mean, the ones who do this not by incident, but by purpose. So we took the probes with both resolvers hijacked. We drop ASs with less than 3 probes with hijacked DNS. That is, we try to drop incidental observations or just errors of our classifier. And here are just the top 3 results: Telecom Indonesia, Vodafone Italian, British Telecommunications, which don't belong to some oppressive government, which shows that DNS hijacking is not necessarily used for censorship, but it may be also used for different purposes. I don't know, like making money out of I don't know, some advertisements, for example. So just we should be aware of that, there are different motivations for that. So conclusions, DNS hijacking is a real thing happening on the internet. I think that most of you know this, but we provide the data. We did an open source implementation of that, so anyone can build upon our work. There are some countries in the world that have more than 25% or even 40% of chances of the DNS being hijacked. On average, that's more than 1%. The risk does not necessarily come from a government or from a state actor, I would say. Some IASs have like a policy of doing so. So many hijacks were in developed countries. And finally, there is no big difference for Google and OpenDNS. So if you found that your Google DNS resolver was hijacked on a network, just switching the IP probably will not help you. So definitely we need a more secure internet, more secure protocols between the stub resolver and the recursive resolver. So I'm very happy of the Deprive working group taking place here. So hopefully we'll have more secure DNS soon. For future work, obviously we missed IPv6, I mean querying the resolvers over IPv6 just due to time. We planned this. We want a better ground truth method, and we also actually want to analyze the data returned from hijacked resolvers, like where are the IP addresses for non-existent domains in the world. We found something like probe ID in Indonesia that was redirecting non-existent domains to China, which was very interesting for us. However, we still need some more time, and hopefully finally we'll publish a paper. Thanks very much. That's all I had. I am happy to take questions.
Thank you very much. And we already have questions, and more people are coming up. So Aaron first.
Aaron Falk, Akamai. I want to encourage you to publish this as somewhere so I can share the link to your work. This is very interesting work. I have two questions. One, I was surprised to see that round trip time was on there, given the use of things like Anycast for DNS. I'm wondering whether you found that Anycast was a factor in your measurements. And then my second question is, did you look at whether the contents of the response changed? I mean, was this just interception, or was it actually data manipulation? And did you filter out the data manipulation ones, or how is that folded into the results that you have?
Mm-hmm. So for the first question about Anycast, as far as I know, both Google and OpenDNS are Anycast operators, so we kind of couldn't compare it. So I'm not aware about any factors of Anycast that are influencing RTT. So I'm not sure how to answer that. As to the second question about the replies, we haven't had time yet. So that's future work, unfortunately.
Okay, thank you.
Thank you.
Hi, Colin Perkins. I suspect this is another thing for the future work, but did you do anything to look at the replies and be able to try and infer what the reason for the hijacking was? I mean, is there anything you could possibly glean from that?
Yeah, that would be totally interesting, but yeah, as you said, it's probably for future work, and actually it's hard to think of a source of information that would give us answer to such a question. What was the motivation? Maybe, I don't know. I have to think about this.
Sure. Okay. Thank you.
Thank you.
Janai Iyengar, Google. Thank you for presenting this. This is very exciting work, and I agree with Aaron that you should absolutely publish this. The results are really cool. This is perhaps more future work ideas also. Have you considered calling up some of these ISPs and just talking to them?
Yes, we are thinking about it. So yeah, it's future work.
I would encourage you to do that.
Yeah.
I've have experience with having. So our team, we've talked to some of these people, and they tend to be usually not clueful about the implications of what they're doing. So you can find them quite open and willing to share, because they don't know why they're doing what they're doing, but they're willing to tell you what they're doing, which is what you care to know. So yeah, I encourage you to call them, at least try it out.
Okay, thank you very much.
Hi, Pavel, great work. Giovanni Saidian. So I also came across this problem with RIPE Atlas before, and we filtered the results out in a different way, and I wonder what would be the difference between that. So when there was the root DDoS attacks, 2015, yeah, you can also download the data from the roots, and they have some sort of standardized chaos query answer. So you usually have the site name, and what I noticed is like the hijack probes, they change the chaos query answer, and they have a very short RTT. Even during a DDoS attack, when some servers were down, you can actually see you get an answer which are totally hijacked. So what I'm trying to say here, if you just would use the public measurements, let's say for B root or C root, whatever, that they have standardized chaos queries, and the ones that are hijacked, they return different content for the answer, what would be the difference between your method and just this other one that a lot of people have used before?
Yeah, that's very interesting. That's very interesting.
Do you have any? Does your method could like show more hijacks than this simple other one? I'm just wondering.
Well, we would have to compare that. I mean, the data is open. We publish the probe IDs we believe are hijacked, so it would be pretty easy to run more measurements.
All right, thanks.
Thank you.
We have time for one last question, and then Pablo, you can help and give it.
Hi, Steiner Web. Yeah. How did you split your data set into training and validation?
We did it 30 times randomly, so we randomly split evenly into training and testing. So.
Okay. Did you perform any cross-validation?
Not yet, but it's on our track.
I've got a question from Java. It's from Simone Ferlin. Maybe related, would it also be interesting to see the user experience from these hijacked requests?
Well, yeah, definitely, but how should one collect such a data, I would say. But yeah, definitely. Maybe using some crowdsourcing, maybe that's an idea.
Thank you so much.
Thank you very much.
Okay, then our next talk is Pablo, also on, not also, sorry.
Also about the internet.
Yeah, also about the internet. No, there was previously was something on IPv6. So this is on IPv6 trace route and rate limiting. Go ahead.
Pablo Alvarez, Akamai. This is work I did together with Florin Opre and John Rula. And let's go to the first slide. Wait, I'm using this wrong. Here we go. So traceroute is an essential technology for understanding the topology of the internet. And when you're trying to deliver lots of data to people all over the world, you kind of like to understand the topology of the internet. So we do a lot of trace routing. And we noticed that the data we got for V6 was not as good as the data we got for V4. So I'm going to tell you a little bit about that. Then I'm going to tell you how we looked at the characteristics of this data loss, some of the things we tried to do to get better data, and finally some suggestions about what we could do as a community to make things easier for those of us using traceroute. So let's start. How much worse are IPv6 traces than IPv4 traces? I'm going to show you some data from 1 day of tracing, about 20 million traces to 200,000 IPv4 and 100,000 IPv6 targets from about 8,000 vantage points. And this is the data I'm showing are, if you look at the whole trace from the beginning to the last valid router, how many null routers are there on the trace? What is the proportion of missing answers from the beginning to the last valid router? We don't look at nulls after the last valid router. And so what you see here is that for V4 traces, the peak, you can't see this, the blue line is the V4 traces. For the V4 traces, the mode of the distribution is around 3 or 4% missing hops per trace. For V6 traces, it's around 10% missing hops per trace. So that's really much worse. This is averaging over targets. If instead of looking at all the traces to a target, you look at all the traces sent from a particular location, you see something interesting, which is that for V4, we get the same kind of curve with most, the average loss being about 3%. For V6, there are areas where the average loss is about as bad as V4, and there are some vantage points where the average loss is much higher. So this was comforting to me because I was looking for a bug in our implementation, and this says, well, actually, different areas of the internet react differently, and my code is the same. So with any luck, it's not our code. That's the problem. It wasn't our code, and in fact, it turns out the problem is an RFC. So the RFC 4443, which makes recommendations for ICMPv6, states that routers must rate limit ICMPv6 error packets. And the way traceroute works is that the information we get back is from hop limit exceeded ICMPv6 error packets. So if the router doesn't want to send those back, we're going to get holes in the traceroute. The RFC also explains how this is supposed to happen. They recommend a token bucket rate limiting system. The basic idea is that in order to send back an error packet, the router needs to have a token on hand. It starts with a bucket full of tokens, say 10 of them, and so your first 10 probes will get back the data, and then after that it refills the bucket at a specific rate. So for example, if it refills the bucket at 10 hertz, after the first initial burst, you will only be able to get back information 10 times a second. So if you send more trace routes than that, too bad. So the next thing was to look at these rate limiting characteristics. So again, you can do this by sending packets very fast. In this experiment, we did send packets at 10 milliseconds intervals to the same router and looking at what you get back. And if things are reasonably clean, you'll get back something like this. And the clump at the beginning can let you estimate the bucket size, and then you can estimate the rate limit from the rest of the diagram. And we did this for about, let's see, about 3,000 routers in 6 continents. We separated out North America and South America into separate continents. And this graph shows the estimates of the refill rate. And what's interesting to me about the graph is that the peaks are the same for all the continents. So wherever you are, you're going to see a bunch of routers, about 20 to 30% of them rate limiting at 1 hertz. You're going to see on the order of 10 to 20% of the routers rate limiting at around 10 hertz. About a third of the routers that don't seem to rate limit, at least at the 100 hertz rate we were testing them. So this suggests that either operators all over the world have agreed on what the best rate limits are, or more likely that the router manufacturers have set some defaults and nobody ever touches those defaults. And when I talked to people at Akamai who work with routers, they said, oh, no, we don't touch those defaults. So this graph shows you the bucket size measurements. It's a little bit noisier, but it shows essentially the same profile, which is you get big peaks that are consistent across geographies. Okay, so given that we have this rate limiting, and that some of the rate limiting is really hard at 1 hertz and bucket sizes of 1 or 2. What can we do about it? There's a couple of tricks you can play if you're the person running the trace routes. And I'm going to talk about them. And again, this is just proof of principle stuff. We have not tried to optimize these things yet. But here's some data. The first thing we tried was to change the order of the TTLs. The simple-minded way to do the trace route, to do 100 trace routes, is you send 100 packets out with TTL1, and you wait till they come back, and then when they come back, you send 100 packets out with TTL2, and so on and so forth. This is the absolute worst way to deal with a rate-limiting router, because you're going to hit the rate limit on your first router, then you're going to hit the rate limit on your second router, and so on. And even as it spreads out, you're still going to hit a lot of rate limits. So you can change the order in a number of ways. We tried 3 different ways. One is completely random, kind of like what YARP does. 2 is staggered across targets. Oh, sorry, I forgot to explain the colors. Black is the first packet that goes out, blue is the second packet that goes out, red is the third, and green is the fourth. In this implementation, they go out every 2 seconds, more or less. But the point is, so the second is staggered across targets, and the third is you pick a random starting point for each target, and then you just keep going forward from that starting point. And it helped. So in this graph, blue is the baseline method, and that's set at 100%. And then the other three, the light blue, green, and red are the other three methods. And what you can see is we get more valid routers if we change the order of the TTLs. So this is comforting, up to maybe a 20% increase. We get fewer null routers with methods 2 and 3 and more of them with method 1 because the random method hits everywhere, so we're not stopping traces when we see too many null routers. We get a few more completed traces, but this has a cost, and the cost is time. It turns out the original method is the fastest way to get data. The random method is essentially too expensive for us because we're trying to do a lot of traces. And method 3 is a little bit slower than the baseline method and gets us more data, so that's what we're working on right now. Another way you can try and fix this is to use data you already have. So if a router refuses to send you a packet back, it's because it has already sent a packet back to someone, right? Its bucket is empty. So with any luck, you're that someone, and you have that data somewhere in your last few traces. So if you're willing to save the data and search through it and ignore for a moment the issue of load balancing, then you can fill in traces with previously known data. So for example, if you have the triplet ABC in one trace and the triplet CTU in another trace, then in this third trace that has 2 holes in it, you can fill in those 2 holes with B and with T. You need to be careful. You can't hold on to the data too long because the topology does change. Again, there's the load balancing issue, and sometimes you just don't have the data because the router sent back that packet to somebody else, not to you. So how much does this help? Well, let's look just at the orange line. The orange line shows the percentage of missing hops in traces that we are able to fill in. We can almost always fill in the first hop, and we can fill in the second and third hops pretty effectively. Even after that, we can fill in about a third of the hops, up to 10%, up to hop 10, and we can fill in somewhere between 10 and 20% of the hops between hops 10 and 20. So this is useful. This, it does improve our traces. The other method is also useful, but this still leaves us doing worse than V4. So in summary, if you do many traces on IPv6 at the same time, you're going to hit these rate limits. The evidence to me suggests that the rate limits we see have been set at the factory defaults and have not typically been touched by ISPs. We've tried a couple of ways to get more data, and they help. But part of the reason I'm here is to make a request. And so the request is based on the idea that the example in the RFC suggests a 10 hertz refill rate and a 10 token bucket. And that RFC is more than 10 years old. So I think our hardware has improved quite a bit since then. So a rate limit of 100 hertz refill rate and a 50 token bucket seems relatively modest, something that most hardware is not going to complain about. This isn't just a problem for people doing trace routes. I was talking to Johanna Ulrich from Vienna, and she's been trying to do some research using host unreachable and network unreachable error packets, and runs into the same problem, which is that the routers will tell her some information and then they shut up. They're like, nope, we're done. You can't have any more. So if you're making routers, please set your defaults a little more generously. And I don't know if Russ White is in the audience. I'm going to email him. But if you're writing an RFC that tells people what V6 routers should look like, mention this and mention that the rate limits should be significantly more generous. That's my request.
Can I quickly have a question? Are there any default values in the RFC that are recommended?
No, there are no recommended values in the RFC.
Then Jen. Thank you very much.
Jen Linkova, 2 comments. One of the problem here is there are default value which you could change, but plenty of routers have hardware limitations which you could not change without replacing your hardware, right? And indeed, in IPv6, the situation with sending ICMP back will be much worse than before because of you do not know how much ICMP packet too big that router is sending already to other hosts. And the second problem, if a vendor has a common limitation for all ICMP and rate limiting all ICMP, it potentially, you might also be affected by neighbor discovery. So yeah, obviously, I'm not surprised to see that IPv6 is worse here. And administrator not always could change those defaults because it's hardware dependent.
Michael.
Yeah, Michael Abrams. So, did you try changing your source address when you send so that the router sees different destinations to send back the error to?
I did a very quick and dirty experiment on this, and it looks like the rate limits are per router, not per source,
or at least per port, or something like that. So it's not.
Well, these are ICMP traces, so it wouldn't be per flow. Or I mean, yeah, it looks like the limitations are per router.
Well, I don't think you can make that leap, but because a lot of routers will actually, like the line card CPU is the one creating the error. So it might be per line card or they might have several of these, but it might be generated by the MPU. So it's not per router, but okay, never mind. What was the second thing? Okay, so there was an earlier graph. Did you differentiate between getting 0, 1, 2, or 3 responses from a router when you're saying you're getting no response? I didn't understand that from the graph.
We are only testing each hop once.
Okay, because when I heard, so normally the default, for TraceRoute is to send 3 packets, and when we're talking about holes, I thought it meant 0 responses. But so this is like, okay, so you're triggering already on not getting the response from the first try.
Yes.
Okay, it would be interesting to see when you're doing the traceroutes if you're actually sending multiple packets where you're not getting any response. But because I thought the graph there, it looked like you were sending 3 packets in the colored, very nice, very a lot of color slide. So, but you were not?
No, this is not the default traceroute implementation.
Andrew McGregor, having worked on a few V6 routers implementations, it's quite likely that there are a lot out there with much higher limits than you are able to detect, but still limits. And these are probably set not so much by processes in the routers, but by communication between the forwarding plane and the control plane. And you're likely to find that actually, despite the CPU being really quite fast, there isn't enough there are not enough packets per second available between the control and forwarding planes to actually get the limits higher. And so you find limits in exotic places inside the router chassis. Also, to the previous point about line card CPUs, yeah, it usually is the line card CPU doing this.
So I didn't completely understand what you said. Are you saying that there are additional rate limits beyond the token bucket that we haven't seen because we were not going fast enough?
Possibly, or possibly that the limit is not actually a token bucket, but a packets per second limit somewhere inside the router implementation, and it's for such things as all ICMP or all packets destined to the control plane or something like that.
The data I got are consistent in most cases with a token bucket, at least for the low rate limits.
That would be a normal way of implementing such a low limit, yes.
John Brzezowski, one of the things that I think is important to note is we often, I work for Comcast, so for largest V6 deployments, we often do things that you see deliberately because ICMPP6 can have some pretty unfortunate side effects as far as the stability of the network is concerned. It would be interesting to run this test. So there's this notion of like the internet and then stuff that's not the internet, like internal. It'd be interesting to run this internally from within a network to see if that changes the view or the vantage point for how the traces are permitted or not, or rate limited or not. Mm-hmm. The other thing I wonder, as I sat here and I listened to a few comments, is addressing, right? And then, like, do some people use, addresses that prevent you from getting an addressing methodology that prevents you from getting a proper response back, right? So maybe links aren't using globally routable addresses, for example. I don't know. I don't know if there's anything in your data that would suggest that or not.
So I did not, I know that in V4 traces, we often see RFC 1918 addresses. These data, if we get any kind of address back, we count that as a valid hop. So I was not filtering out non-globally routable addresses. So again, it depends how things are set up, but I can look in the data for that. I didn't think to look for that.
Sure.
Thank you.
Thank you.
So before you run away, did you just say you want to run some trace routes and give the data to Pablo for further analysis?
I could actually do that. Yeah. I mean, I could. I mean, I work with a lot of other people from your company, so I mean, look, find me after the meeting, we can talk. Sure.
Thanks.
So just on a comment on the rate limits and stuff, Andrew Dogan on Nokia, from somebody who actually wrote some of that code. Unless you have a low-end routers, then yeah, you're upgrading hardware. But like if you have a decent router that is just a software tune-up, if you're tracing on a port or an interface, you're going to get a different limit if you spread your traces over the line card. Line card CPU does, but not often takes. There are architectures that don't use line card CPU, centralize everything. Mm-hmm. If you have slices on your line cards because the vendor doesn't have a big enough CPU, then if you go on a single slice, you're going to have a different limit. So you have to be careful how you're going to get that stuff. You will be hitting limits. You will be hitting limits from ICMP at some point. Those are usually software imposed limits. They so can be tuned. You will be hitting the limit if you're going to send everything is ICMP test. Mm-hmm. You're going to hit some other limits. If you want to have really what can be done and how you should tune, you should probably talk. It's not secret. You should talk to some of the vendors who are in the room, and we can tell you how to do the tests.
Thank you very much.
And at the end, if you want to do more, then at some point, yeah, you may need a better CTM card, but the better control card. But anything there that's like 2-3 years old, I don't think you have any concerns. It's really the old hardware that you would have a concern.
Yeah, I'd like to know, Olivier Bonaventure, I'd like to know if the data that you collect is publicly available.
I'm not sure. Talk to me afterwards.
Yeah, because there are many projects that collect trace route data, so Kaida, RIPE Atlas, and I think if we do together the project that collect data and we put the data publicly, then it will be a less incentive for other companies to try to collect private data. And if we have a good data set of trace route data, then we will have a good data set that will be available for everyone. And so if you could join together with RIPE Atlas, Kaida, and others that are providing public data, then everybody will have public data about trace route, and nobody will have to write their own trace route tool to get private data.
Yeah, I think that's a very good proposal. Thank you for the talk.
You're welcome.
And at that point, we go
Thank
on
you.
With Dave. Also, this time also about IPv6.
Yeah, right this time. All right, I'm not in my chair role, so be meaner or nicer to me than you usually would. This is about work that I'm doing in Akamai about taking a new measured approach to the way we might do IPv6 address anonymization. Arthur Berger, my colleague, and I have a short paper about this that's available to you now at archive.org at the URL there. So we're going to talk about a really simple kind of IP address anonymization, just anonymization by truncation or aggregation, where we strip off the trailing end of the IP address, and considering what the consequences of that are. Is it providing any kind of anonymity at all? Is it providing a similar kind of anonymity to what you might see in V6 or V4 if you strip off something that like the last 8 bits or something? And why is this used? Well, certainly in my company it's used for things like web analytics, but you can imagine, and Google Analytics does this as well, you want to be able to match the activity that you see in the internet to network topology, to routing, to the service providers involved, and geographic locations. So if you didn't leave a public top portion of the address, you couldn't correlate easily to those sources. So just a real simple example of what this would look like in IPv4, and I think probably something you've seen before. Here I'm showing you 32 IPv4 addresses in the 10.0.42 subnet, and each of them has some counter associated with this. In this case, it's just an occurrence, like maybe they will, on or off activity. And the anonymization is simple, right? It's just you truncate to some fixed prefix length, like here it is /27, and say, well, I've clearly combined the activity of 32 addresses, maybe 32 actors, into 10.0.42.0/27, and someone would feel, well, maybe I've been anonymized somehow if I've been included that way. And a lot of this has been going on for decades. That's a common way to anonymize. So I'm just going to start from as if we didn't know anything or feel we knew anything about what was the right level in V4. Well, truncation-based anonymization is only ideal to use if you can guarantee that it improves privacy. So I'm wondering, from a measurement scientist perspective, can we tell if it improves privacy or not? And I have, my position is that clearly it's going to be different in V6, because V6 addressing is very different. So we're proposing something called KIP anonymization, where K is the number of members of an anonymity set that we're saying we're going to make an individual appear to be indistinguishable amongst K individuals in that set. And it's based on the notion of K-anonymity that you might have heard of before from the medical world or health records, where you say, I can prove that I've mixed these in a way that you can't discern which of the patients suffered this particular problem, for instance. That's the sole connection, though. It's just that I use the same letter K. It's not the same kind of proof. It's a very different kind of proof. And by the way, it also happens to be very similar to the definition in RFC 6973 about privacy considerations for internet protocols. So we're going to use some real data in this study, 4 sets of data. The first one, a meeting network, a meeting that happened earlier this year, happens to be IETF98. And then we'll talk about 3 different ISPs that happen to be in 3 different continents, but I chose them not because of that, but because they have interesting characteristics. For instance, a common practice today is to say suggesting anonymizing IPv4 addresses to the /24 level, so stripping off the lower 8 bits. In IPv6, a very common recommendation is to strip it to the /48. Now, in this particular network, the Japanese ISP, if you look here, over 7 days, we see the same number of active /48 prefixes, meaning the ones that cover World Wide Web clients in that ISP, as we do /64s. So clearly, if I truncate from 64 to 48, I'm not anonymizing anything at all. And this was sort of my inspiration initially. Clearly, I know that /48 based anonymization is doing nothing in some cases. But there are other networks where just this US ISP and the Japanese ISP, very disparate numbers, right? On the order of 300 times different in terms of the number of /48s they used to cover. So just evidence that there are very different addressing schemes, and we want to accommodate that in the anonymization mechanism. But we can see that in this case, the Japanese ISP and the US ISP, in terms of /64s and full addresses, they look very similarly sized. So that's curious. But if you look at this European ISP, which I've been told you which they are, but I don't have any reason to believe they're differently sized. They're using twice as many full addresses in a week's time and 10 times as many /64s. So just give you an idea, there are very many different addressing schemes used in the V6 internet today, and an anonymity mechanism that doesn't take that into account is probably dangerous. So KIP just has 3 steps. The first step is I'm going to call temporal and spatial address classification. Then we're going to move on to activity matrix analysis. And then the last step is called anonymous aggregate synthesis. We're just going to make a table of aggregates that we suggest that would provide some guarantee of anonymity there. So let's look at what these steps work like. The first step classification, I called it address dendrochronology. Dendrochronology is the study of tree rings and branches over time. That's how one of the ways that I think about IPv6 addresses. I presented this last year, so we'll just go really quickly with what that was about. If you take a set of v6 addresses, for instance, World Wide Web clients, I'm showing an abbreviated version of 1,600 of those addresses on the left there in the green and the red. And I can take those addresses, they just have the colons, missing, or it's just a fixed length version. We can classify those addresses and say we have a spatial characteristic amongst them. If I sort the addresses, I can find the first bit at which they differ. And this tells you essentially, it's a measure of how far apart the addresses are from each other. And you can imagine for pseudo-random portions of the address, they're randomly different distances apart, and they're quite far apart. So that's the spatial characteristic of the classification. The other classification we can do is, since we're sitting at, let's say, a web server, we can see those addresses come back to us or not over time. That's a measure of stability, a temporal characteristic. So we have the number of days stable. In this case, the last address was seen across multiple days, and the ones that say 0 day, they might have been temporary ephemeral Slack privacy addresses. And then lastly, a kind of a really neat, simple way, a nice way from Fernando God's IPv6 toolkit, you can classify an address by pumping it through this tool, and it will tell you when it knows about the address. And in this case, the tool is saying, I think that address you gave me is randomized in its IID. So that's sort of the starting point. We say as a foundation, if Fernando's tool says it's randomized, let's start there and see if we can use those randomized addresses, the privacy addresses, as a way to unravel how many devices might be in that prefix. So the question then is simply, do I truncate at the /64 boundary? Would you be satisfied with that? Probably your service provider is giving you a /64, so the identity that you're being assigned by your service providers isn't completely captured by the /64. So we're not going to be satisfied with that. Well, are we satisfied with what length, what prefix length would you be satisfied that if we truncated to there that somehow you were anonymized? Now let's move on to step 2. That's just a base classification. We have all the addresses, they're classified up by those metrics that I told you about there. Now let's look at we call an address activity matrix. And this thing that looks sort of like a punch card here, the red represents bins of time, in this case hours, where an IPv6/64 address was seen active, and vertically in this matrix is just progressions through the address space. So we can see patterns of activity there, and by studying this activity, I can discern some things about the way the addresses are used there that I'm going to use for anonymity. This is based on earlier work we did just last year with Philip Richter, who's presenting, by the way, this afternoon in the IRTF Open meeting. But the simple idea is you make a matrix and you have time in the horizontal dimension and space in the vertical dimension, and you just fill in cells where interesting activity happened. So that's what we did for IPv4, and we're able to discover patterns of behavior across the entirety of the IPv4 address space. But I want to take this notion and carry it into IPv6. So what Philip saw was things like, which parts of the address space seem not to be used on the web. These angled ones in the upper right show, for instance, DHCP pool activity, and the one in the lower right is a very heavily utilized address block. So clearly this visualization offers some analytic capabilities. Now let's turn to v6 here. So because I'm older than Philip, I'm going to use ASCII art instead of PNGs. The other reason I'm going to use ASCII art is the space for v6 is really big. So if you try to make a PNG file that expresses the entire space, it's going to run out of memory on your machine. So the characters here, well, let's start first with the addresses again. So just like before, I've got the /64 prefix there in green for a set of addresses, just 16 addresses here that happen to be observed in one day in one /64. So this is the typical home situation, right? You've got a /64 here for home, and throughout the day, 16 addresses were used. Those are the interface IDs in red. Now the next thing we're going to do, and I'm going to point you to the paper for details here, but I'm going to tell you that we can use probability to try to discern whether or not those IIDs are plausibly random or not. And it's like the birthday problem, right? Like if you've got 16 people, what's likely that their birthdays will collide? Well, if I have 16 ostensibly random numbers, a certain number of bits leading them is likely to collide. And I can just play that out in advance and figure out what it is. But in this case, I'm saying those 16 addresses are plausibly random in their interface IDs because that spatial characteristic, the distinguishing prefix length, that I have in the second column there is less than a predicted value. So I'm just going to ask you to assume that for now if you look in the paper for the proof of how that works. So space and time again. All I did was space goes the other way from top to bottom. And now what do we, so the hash marks here are the places, the cells that are filled in. That's where the web server saw activity from that address, right? So the question is, you'd say, Dave, I see 16 addresses over here over a day. Can you tell me when was the address, the prefix assigned to a user? When does it appear to have been assigned? And can you tell me, for instance, how many devices might have been using those addresses? Well, the first thing we can do is we can take that activity and sort it left to right based on the initial activity of that particular address. So they have the idea that, it's in your home, you've got a mix of different V6 capable devices, and throughout the day, they move across these seemingly pseudo-random IIDs. Now, the next thing I can do, and this is the key to the whole technique, if I see, for instance, in that fourth line, I filled in with these red @ signs, I saw an instance of activity at 1 hour, like the 8th hour of the day, and then again in the 13th hour of the day, but with that random number. So the inference I'm going to make is that address must have been signed, even though I didn't assigned to some device, even though I didn't see activity between it. So I'm going to extrapolate from those two observations of activity that it was assigned throughout that duration where these @ signs are. We'll talk about that a little bit more, but that's the key to the technique, is that privacy addresses allow you to draw conclusions about when they must have been assigned on equipment, even when you don't see activity from them. So then we're going to annotate this matrix a little more. So instead of just having the pixels, it's got a couple different characters. And these X's and greater thans and less thans, they're showing the beginnings and ends of episodes of activity from some observation point. Do you have a qualifying question, Tim?
Oh, no, it's a question. It's more of a question about your assumption. So I'd leave that to the end.
Do you mind if we leave it to the end?
Sure.
Just because I got a lot of things there. So, okay, so we're seeing these episodes of activity, and if I see at a point in time there's activity, and another point, I'm making the assertion, which Tim and I will talk about it at the end, about is that a valid assumption to make? So now we can do an interesting thing, right? I can do some kind of funny arithmetic on these characters I put in this matrix and say, well, if I saw two devices that in the same hour's time, that 3rd hour of the day, at some point in time during that hour, those two are active, those two X's add to 1, meaning I know at some point during that hour, at least one address was active. I can't say 2 because I don't know that they were active at the same moment, okay? So that's why the funny arithmetic is here. So I play out this kind of arithmetic and I get an array of totals, and the conclusion is, from just this sparse activity in this particular /64, I can see that there was some moment during that day at which 3 simultaneous pseudorandom IIDs were assigned. That's the maximum. So that's an interesting measurement result in and of itself. Now let's take that and see what we can do with anonymization as a result of it. So what we're going to do is take that, now that we looked at the activity of individual full addresses, or these interface IDs, really, I already proposed to you that the /64 is the thing that's tied to your identity. That's probably the thing that your network gave to you as your identity assignment. So let's just take that activity matrix and percolate it up to say, when was the /64 assigned? And that's this array of exclamation points, and then I turn into a Boolean array of values. Where there are ones there, I have gathered evidence that the /64 is assigned to someone. And where the zeros are, I don't have any evidence. It doesn't mean it wasn't. I just don't have any evidence from the observation point. And we're going to call that, these moments between the 24-hour bins, we're going to call those fence post moments. So what I'm trying to do is jump from activity in an hour where I don't know exactly the moment to saying it must have been assigned in one of these 23 moments that separates the 24 hours. And that's the second key to the technique. Being able to count at a moment. Now, the way that works is, consider these yellow boxes are those hourly bins. The fence post moments, just like a fence, are the moments between them.
You have about 5 minutes left.
Thank you. And then when we look at activity on either side of a fence post, if it's the same address, we can conclude that there must have been one address available at that fence post. So what I'm doing is building a matrix now with a fence post that says it's okay for me to add the values together because they happen at the same moment across addresses. So we get to the bottom, we get this array of values, and now we're ready to move on to the step 3, the last step in synthesizing anonymous aggregates. I'm going to take those values for all the hundreds of millions of /64s we see in a network or in the entire internet and build a tree where now, just instead of having only one counter in the tree, this is a Patricia tree or a base 2 radix tree, I'm going to have an array of whatever size my window of observation is. For this trivial example, I'm showing you 1 day, but in practice we would use a week or 2 weeks. And there's 23 values. So now, again, I'm going to go a little fast. This is explained in the paper, but basically you could imagine pruning this tree and aggregating those arrays of counters up such that, for instance, those first two nodes at the top, they would aggregate to that /55 with all the 2s there. And what I'm saying is that if I aggregate to the /55, I have evidence that two /64s were simultaneously assigned at those same moments. And if I had a really compromised notion of anonymity that said it was sufficient to just mix two people's traffic together and you'd consider that anonymous, that's what I've just done, is produced an anonymous aggregate prefix there. And then it turns out in this case, because I was using the IETF meeting network, there were so few 64s active that it turns out that's the only one I can report with the criteria that k equals 2 /64s were active simultaneously. So now let's jump kind of quickly into, so I take that, I had a characterization of the data sets before. The part in bold is these counter conclusions from that algorithm that I just described. And the cool things we can see here is for instance, that we had a network that had, in 21.4 million active /64s over 7 days, but by that counting mechanism, we only saw 2 million at a time. So I'm saying a reliable lower bound estimate of the simultaneous number of identities assigned in that network is 2 million. And remember, we talked about these three ISPs having very different characteristics based on address counts. If you use this mechanism, it shows that within a multiple of 1, they have about the same numbers of simultaneous users. It means we've seen a fence post moment between hours over the period of, in this case, a week, that shows that those three different networks are about the same size. And now we can use those counters to go and produce aggregates. So to finish up, now let's say we decide that mixing 32 IPv6 identities together in a report that maybe my company's going to publicly release or your company's going to publicly release, we say 32 is enough to mix together. K can be anything, right? You can say 256 or whatever. But when we run those numbers for the US ISP, this is the distribution of size of these anonymous aggregate prefixes we get. So compare this to what I think is status quo today. People use /48 aggregation. This is saying if instead of using /48 aggregation, you use the thing that Plonk and Berger developed, you can sometimes share /50s. In fact, most often you can share /50s because they meet your guaranteed requirement that it mix 32 identities together. However, in the EU ISP, /48 is not usually sufficient. More often you have to go to 47, sometimes you have to go to 41. So you're going to get an array of different sizes of anonymous aggregates out, but those are the ones that meet the guarantee, and the 48 that we might be using today doesn't meet the guarantee, meaning we don't have good evidence that it anonymizes individual users in this V6 network. Lastly, the Japanese ISP, which arguably had the most unusual high order bits in terms of their aggregation, /48 never met the criteria. You never mixed 32 users together when you aggregated to /48, but you did very often when you aggregated to /41. So it's a new way to think about aggregation. It's not exactly rocket science. We have the algorithm laid out in that paper, but that's basically how it works. And we went from a place that we just assume, based on like /24s in an IPv4 network, that this is good enough kind of aggregation to say, I have good evidence that I can prove that the aggregates I used actually do mix a certain number of identities in a V6 network.
Thank you.
Tim Chang, yeah, I think this is really good. Thanks, Dave. I'm trying to remember what the question was now. So I think it was about when you were talking about...
I've heard a question related to this before, so I think I might be able to ask your question.
About privacy addresses and 7217 addresses. I don't think you can tell the identifiers apart, whether it's a privacy address or 7217 address from the randomization. But in one case, if you go away and come back, you'll get a new privacy address because you're reattaching. In the other case, you'll get the same last 64 bits. So making assumptions about persistence is different, I think.
Yep, thank you. I think I agree with you if I understand what you're saying. Remember in the third column here, I've got a stability characteristic of the address from an observation point. Now it has to be an observation point that sees a lot of traffic. But if you are where you see a lot of traffic, I can use a sliding window of time and look if I've ever seen that address before. You're right to question whether or not my test for randomness is reasonable. What we'd want to do is say, have we ever seen that value before? Or have we seen it spatially across other networks? Because any of those would suggest that it's not random. Yeah. So the assumption that it was unstated that I guess you reminded me to state is, I'm saying this works if the temporary / privacy address mechanism picks good random numbers, and we can reject the persistent pseudo-randoms by looking at their days stable.
Okay.
Alex Mayer over Nictodati. I really like this work because I think it's important in so many other spots besides like anonymization reports. For example, it would be useful in like rate limiting, especially for example in DNS service. So whenever I want to like bundle a couple of users together or whatever, n users, so it would actually be great if in some way we could take this work from the IRTF maybe to the IETF, so that we could create a protocol, an infrastructure or something like that, where I could identify, I would say, reasonable prefix lengths for all kinds of rate limiting, measurement, anonymization. And the other aspect is the European data protection regulation that comes up very soon.
Yep.
So this is a hot topic now, and this is really, really amazing work. Thank you.
I agree. I think that would be an interesting direction to go. And the thing that you're proposing is, are the results portable? If I observe activity from one point, can they be ported to somewhere else? And I would argue, without having thought about it too much, is they're portable if the place you're porting them from is a place that has better visibility than where you are. You know.
And also, can we aggregate the data if like many people actually do those measurements aggregation algorithm? Can we like publish the results, aggregate them?
That's an idea I hadn't thought of, but that's great. If you're thinking of sharing the result, if you can find a way to not disclose the privacy addresses in the first place, then maybe we can integrate our observations in some private way to get the privacy aggregates.
I mean, it comes with all kind of connotations regarding privacy and, well.
Yeah, that's a neat idea, but there are methods that allow you to share addresses in an opaque way. And tell if they're the same without disclosing their value.
But essentially, there are so many cases in which I have an IPv6 prefix, and I want to know, okay, where do I cut it? Yeah, essentially. And if somebody else has created a measurement that came to a conclusion based on a public available algorithm, that could be shared.
Thanks.
So that sounds like there maybe is some guidance document that we should take, on as a group.
Yeah, well, that would be interesting. Yeah, I think the place I'd like to start is I don't even know where all the places, other than the one RFC I cited, where in the IETF community do you talk about such a thing? So it's a candidate. Maybe it'd be a candidate first draft for.
Yeah, I think we can actually take on such a draft in this group and then bring it to the attention of the IETF when we have it in the right shape.
Okay, and I know I'm over my time, so let's do these quick.
Pablo Alvarez, Akamai. So in terms of reusing these data, do you have some idea of their temporal stability? That is, if you do this experiment and you run it 6 months later,
right?
Do the ISPs still have similar properties? So how often would we need to renew this data and share it?
We don't know that exactly, but you're right to be concerned. The way we develop the algorithm is to run it continually, so that you can, as you're doing the anonymization, you can tell whether it worked or not. But so it works really well and simply for offline analysis. Like you're a researcher and you have a data set that's contained, it was finished last month, you can run it and you're guaranteed that you've mixed them correctly. But if you decide that you're going to use that set of prefixes and forecast into the future, we need to do new work to figure out how long that would last. And
Michael Abrams, so combining this with your earlier work to identify where the addresses are within these aggregation levels, for like there was rate limiting dimension. I think there's some kind of anti-abuse handling group here in the IETF. I think they would be interested in if you can identify like this ISP typically has like a /56 to each customer. So not only like you're going the anonymization way, but also like how do you identify a household where you're going the other direction in aggregation from, to identify that pivot point, or like where is the household? What's the aggregation policy? So for reputation, like identification, so on, it could be a good input for them as well. The RIRs have a way of the ISP publishing this. Basically, nobody does. You could, by doing this kind of measurement, I think create that as well, equal information.
That's a good reminder. What Michael's saying is we can either discover it right or they can tell us a priori. And what I'd love to do is compare the two, right? Anyway, thanks for the questions and the comments.
Yeah, we're a few minutes late, but I think that it's fine. So we're kind of jumping a little bit from the operations part now to more performance measurements, and the first one is on latency measurements. Toke.
Thank you. Hey everyone, I'm Toki Highland Yarrington. I'm a PhD student at Cal State University,
And this study I'm going to present, we presented this at Connext last year. And basically what we wanted to look into was how much buffer bloat exists in the internet. And of course, we don't really have a vantage point to look at the whole internet. So what we did instead was we figured out that there's this thing called MLAPS, which has this really nice large-scale active measurement data set. And then we found a passive capture from an ISP, which has some different characteristics, and we wanted to combine this and see if we could extract some insights from these two data sets. Then, as a proxy for buffer bloat, because you can't really necessarily infer that in all cases, we used latency span as the metric. So that's the idea that if you have a certain path or certain flow, then obviously the minimum latency measurement you get over that flow is sort of an existence proof that we can achieve this latency during on this path. So any other measurements we get in the same flow that are higher than this are to a certain extent too high for this flow. So the difference between the minimum and the maximum seen in the flow is sort of a proxy for extra latency at this flow. And then to specifically look at queuing latency apart from this, we did two things to try to estimate queuing latency. The first thing was that if we have a long TCP flow in the active measurements, we get continuous RTT measurements over this time, and we also get information about TCP congestion events, i.e. a drop leading to a reduction in C-wind. And if we look at the latency right after such an event, in many cases we could see a very distinct drop. I'll show you an example of this a bit later. And we use this as a proxy. So we assume that in these very distinct cases, that this drop actually corresponds to the queue draining while the flow slows down and comes back up. And then on the data set where we knew where the data was from, it was from sort of a link where we could capture it, we could correlate link load and latency and see when latency goes up as the link gets loaded. That's also a very strong indication of buffer bloat. So the two data sets we used, as I said, one was the NDT data set, which they're sort of active measurements where the user goes in and say, I want to test my internet connection, and it will start a 10-second download going as fast as it can. And we looked at these, there's about 265 million total test runs over 6 years. And the data source that we looked at, sort of MLabs publishes these TCP state machine RTT samples for over the whole flow. So we took these and then we got the span of latency, as I mentioned before, within each flow. And then we combined this with this capture from an ISP network, which are two 1 gigabit per second aggregation links with only 50 or 400 customers. So these are way smaller data sets that were collected during a period of time in 2014. For the captures there, we looked at the delay between the SYN-ACK and the ACK. So the intuition here is when a client connects to a server on the internet, it will send a SYN to the server, and then the SYN-ACK comes back, and the client will immediately send the final ACK to establish the connection. And since we are capturing packets on the access link at the ISP, this delay between SYN-ACK and ACK corresponds pretty well to the latency from the measurement point to the client, because we assume that the operating system generates the ACK immediately when it gets the SYN-ACK. So for the first data set, we looked at, as I said, latency span. And if you look at the left-hand side here, you have the, you have the minimum and the maximum RTTs, and you have the RTT span. So what you see here is at about two-thirds of the flows have a span of 8 RTT of latency above 200 milliseconds. And then on the right-hand side, you can see that there's a significant difference. So these are sort of the geo assignments of the client IPs that Measurement Labs provides. So these are not necessarily completely accurate, but they give a nice indication of where in the world are these clients. And the clients will select the nearest server for the test. So it's not like this is because all the servers, all the clients in Africa connect to a server in the US. These are actually connections to the nearest server. And as you can see, there's a very large regional variation between the different continents. So one of the interesting insights we got from this was that if you look at the development over time, you'll see on the left-hand side, the latency is basically the same for all these 6 years of measurement, whereas for bandwidth, as you see on the right-hand side, there's a sort of steady development towards more bandwidth. So whereas bandwidth gets better and better, latency doesn't. And of course, some things you can't really change for latency. I don't think we've figured out how to change the speed of light yet, but there's a lot of other sources of latency other than just propagation delay. And these are definitely not getting better. And like several hundred milliseconds of latency, we should be able to do this better. Yes.
A refrain question, is the same TCP algorithm, the congestion avoidance algorithm, used in all these measurements, or did that change over time?
That's a good question. I think on the server side it's the same one, but obviously the clients, you don't know.
Yeah, because I thought the bandwidth increase could be partly because of better TCP algorithms as well.
So the Toki's correct. The server side, MLab's server side TCP hasn't changed over that span. But yes, the clients may have. So this may reflect partly the change in the distribution of congestion controls in the clients.
Yeah, but we're looking at traffic going from the server to the client in this instance.
Sure, yes.
Right. So that was one of the interesting things we saw, that difference between latency and bandwidth.
Let me just say one more thing. I think Windows XP came with TCP window scaling. I don't remember if that was turned on or not. So that might actually have changed as the client population changed over this time span.
Right. So access network data, where we looked at here was the same span between, but to all connections going to the same customer, the same IP address here. And again, if you look at different, depending on which percentile of all the measurements you look at, you get a span going from 50, 60 milliseconds at the up to almost 200 milliseconds in the for a quarter or more of the traces. So again, like a lot of them do not have a large span, but we can see that there are some connections where we get this variation that indicates extra latency. Then there's the queuing latency thing I was talking about. So this is the pattern that we saw. This is a trace from a single 10-second test where the cross you see at the top is the congestion event. So as the congestion event happens, it sort of it flatlines. So the flat part is TCP not sending anything, so it takes a while until the next sample arrives. And when that arrives, you get this sudden drop in measured latency. And so the size of this drop, so from the flat part and down to the bottom, that was what we used as sort of the indication. This is a lower bound on queuing latency. So for all flows, it's like out of all the flows, we can only detect this pattern reliably in about 5 million of them. And if we then plot the size of this drop for those 5 million flows, we get this distribution. So that sort of indicates that when we actually see this, what we hypothesize is a queuing latency, then it's pretty significant from sort of in the median 200 milliseconds of queuing latency, which it sort of fits quite well with what we've seen in lab tests. Like when you do see buffer bloat, it's usually there's quite a lot of it, especially when the bandwidth is not very high, as is the case in most of these tests. And then this is an example of one of the traces that we saw from the ISP, where you can see the rate on the left-hand side there. This is obviously a 0.5 megabit per second link, and as soon as the transfer rate hits the ceiling there, the delay goes up to more than a second of delay. And we saw examples of this in both of the traces from the ISP. So what we drew from this study is that there's a lot of latency variation in the internet, and it has not improved over time, whereas bandwidth has, for whatever reason. And also that there are significant regional differences, both, as I showed you here, over different parts of the world, but also in different countries within each region. And then at least some of this extra latency that we saw can be attributed to queuing, and where this queuing does occur, there's a lot of it. So, and sort of I was asked to put in some recommendations to this, and my main part is that we need to pay more attention to this, to latency. And I know this is starting to happen, and especially certainly in academia, but also I think more and more people are trying to wisen up to the fact that higher bandwidth is not necessarily in itself equals a better connection to the internet with modern applications. And we do have queue management solutions, several of which have been standardized or in the process of being standardized at the IETF. So it's just a matter of turning it on, and it can really improve things. The CPE space is obviously a place where we need to do this, and where deployment is difficult, but the technology does exist. And then, of course, better congestion control. There's other ways we can try to deal with this problem. Yeah.
Thank you very much. I actually have a question. So did you also, so you detected those cases where you have these large buffers, and when you have congestion, you see a high delay. Did you also try to detect cases where you actually find AQM and identify those cases?
No, not directly.
I'm not sure how you do that, but it would be interesting. And the other point is, I think, so your data is from 2015?
Yes.
So I guess the most interesting part for me would be actually the data from 2015 to now.
Yeah, so the nice thing about NDT is that they publish all the data, and I think it's pretty straightforward to rerun this on newer data sets. So we publish the data set and the scripts we do this with. And
Please do, and bring it to the list.
Yes, I can do that.
Hi, Vaibhav Bajpayee to you, Minik. So if I understood correctly, these are measurements from taken by users towards MLab servers, right? So this is specific measurement traffic towards MLab, which usually content providers are not optimizing for, right? So when making a statement like latency hasn't improved over time, I would also put a caveat that this is actually measurements taken towards MLabs, and it may or may not be true for normal traffic that people actually go to. You see what I'm...
Yes, I consider the fact that this is not speedtest.net, so it's not in the ISP network. I consider that a feature, actually.
So I would also say speedtest.net is also not normal traffic, right? So traffic towards Google or Facebook would be normal traffic, because this is what people usually do on the internet. So has the latency towards YouTube or Facebook improved or not over time? The study doesn't tell us that, right? Mm-hmm. So I would put a caveat as well.
Right, that's fair point, but the internet is also more than YouTube.
Chobin here from Netflix. The graph you show that the congestion events is kind of interesting. Can you go back to that?
Which one?
The congestion, yeah, this one. So you said you discovered this kind of pattern in 5.7 million flows. How many total flow out of that you found those 5 million flows?
And how many was the data set in total?
What is, yeah, data set?
That's 200 something million. So it wasn't a very large percentage of the flows, but that was partly we obviously didn't look at 5 million flows manually, so there's sort of a matter of being really sure that our algorithm didn't, like, we erred on the side of not having too many flows instead of having false positives.
Right, because I think that is a kind of very interesting, because you only find this is roughly a few percentage of your total flows, right? Out of 100 million flows. I think you only see this pattern if this event is sender induced, because otherwise, if the event is induced by cross-track, your congestion behavior will not alter anything at all. So this actually gives you a very good indication. Say there's maybe 80% of the congestion events received by data center actually is not self-induced. That's a possible indication.
So that was another pattern that we saw in some cases manually, which was actually why we started looking at it. Which is also that some cases, there's some of these flows that over the 10 seconds do not get a single congestion event at all, but the latency increases quite a lot. But this was not sort of something we could reliably detect in the dataset. We also filtered out flows that get more than one congestion event over the whole flow.
Okay. Yeah, I just want to point out, because that percentage means the rest of the flow, which you do see the congestion events, but you don't see this kind of pattern. That's most likely an indication of that event is a cross-traffic induced, not a sender induced.
That could be. I wouldn't say that all other flows, like none of the other flows, have self-induced congestion events. As I said, we've been very conservative with the detection algorithm here, okay. But obviously a lot of it is for a lot of these flows. That's true.
Okay. Yeah.
Thank you very much. Very quick.
Yeah. Thanks, Gareth Tyson. I was just curious about how MLAP evolved during your measurement period. Were more servers being deployed, and was there certain geographical bias that may have influenced the findings you had? For example, I know Africa has a very small number of MLab servers.
Yeah.
And that's grown a lot over the last 5 years.
Yeah, I don't know.
Okay. It was a quick one.
Yeah, thank you. Weibert is next. Talking about YouTube measurements, this time again with a focus on IPv6.
Hello. Hi, so my name is Vaibhav Vajpayee, and I'm a postdoc at TU Munich, working with Jorgot. And so today I'm going to talk about measuring YouTube content delivery over IPv6. And so this paper has been recently gotten accepted and will appear in SICOM Computer Communication Review in the July issue. And but the paper is already online, so you can click on this link and you can see the paper as well. And this is joint work with Saba from Aalto University, Jörg Ott, TU Munich, and Jürgen Schoenwalder from Jakobs University Bremen. Okay, so IPv6 is happening, and Comcast tells us that IPv6 contributes to 1/4 of their traffic within Comcast, but this would be higher, I assume. This is data that I have from 2016. So I would love to know the new number at some point. And Swisscom also reports that around 60% of the IPv6 traffic that they see is actually YouTube. So it's more than half of the V6 stuff that you see within the access network is YouTube. And that's so most of the V6 traffic is largely dominated by YouTube, and it's also seen by people in academia. And this is largely happening since the World IPv6 launch day. So we started wondering, so do users experience benefit, or do they suffer from streaming YouTube videos over V6? And in order to do that, we developed a test. We call it the YouTube test, and it's written in C. And we deployed this on Samnose probes. So Samnose, if you know, it's a company based in London, which is handling out probes to people for doing broadband measurements. And these are hardware-based probes, which are largely TP-Link routers flashed with a custom OpenWRT relay firmware. And so this is a deployment of the around 100 dual stack Samnose probes that we have at this point, and it's covering around 66 different origin ASs. And some of the people in the room are actually hosting this probe for us, so thank you for that. And most of these probes are largely sitting in residential settings. So these are measurements mostly taken from home networks. And we had this test running on these probes and since August of 2014. So we have more than a 2-year-long data set. Okay. So these are all the contributions that we provide. So we saw that Happy Eyeballs, which is RFC 6555, that it makes clients prefer streaming YouTube videos over IPv6. But we saw that the performance when streaming videos over V6 is actually worse, both in terms of latency and throughput when compared to V4. And moving away from performance, we also saw that stalling, which you see when streaming videos, is fairly low, both over 4 and 6, and which is why the bit rates that you can reliably stream are fairly comparable over 4 and 6. And although stalls usually don't happen, when they do happen, the durations of the stall are actually higher over 6 than over 4. And all of this is largely happening because GGC nodes, which are Google Global Caches, these are caches deployed within the ISP's network. Most of them are V4 only, at least from the vantage point that we are measuring from. So this is the first study, which is measuring YouTube content delivery over IPv6, and I'm happy to show you some results. And so this is the methodology. So I'll take a different approach. I'll show you the methodology and partially as we walk through the presentation, and you will also see the results in parallel. And we'll go through this using a sequence diagram. So in order to measure YouTube, you have to identify what destinations you want to measure towards. So YouTube provides us an API, which is a V3 API, which is pointer 3, and gives you the popularity of global popularity of videos. So we use that list and we apply our selection criteria that a video should be at least 1 minute long and should also be available in HD and should not have any regional restrictions and stuff like that. And we update this list every 12 hours. And the probes are actually pulling this list from the SAMNOS backend. Okay. And we do this every 12 hours, so you can actually see the profile of a specific video, how it performs over 4 and 6 within this 12-hour period. But we also change this list after every 12 hours, so you can also capture the profile of large number of videos over the duration of last 2.5 years. Note that the test is actually supporting non-wrapped event step-down playout modes at this point only. And by step-down, I mean if you actually experience a stall, the bitrate that you're streaming, you will go down to the previous lower bitrate and try streaming it again. And of course, the results are, you should know that results are biased by our vantage points. So vantage points are largely deployed in EU, US, and Japan, and that's the performance that we see. Okay, so now look at the sequence diagram. So what is happening is when you have this list, you pick up the first video URL from the list, and what the probe is doing is establishing a TCP connection to the website. That's what we users actually do when you go to watch a video on the browser, and it's establishing a connection to the website and fetching the HTML page. Once you have the HTML page, you parse that HTML page and try to see what container formats does the video support and where to get that video from, right? And that's the host name of the media server that is hosting that video. So when you do the DNS resolution from the probe, the resolver will give you the location of the nearest media server, which could be a GGC node if that is available within the ISP's network. Otherwise, you will actually hit a CTN, which is farther away. Okay, and once you do this DNS resolution, you establish a TCP connection to the media server and try to establish 2 connections, once for fetching audio and once for fetching video. Okay, so once you have done all of this, what kind of measurements can you actually see? So the first thing that we looked at was success rate. So how often can you actually successfully do this in the last 2.5 years? So number of successful iterations to total iterations will give us the success rate. And since the test is executing every hour over both address families, you get a higher sample. And what you see is, so red is V6 and blue is V4, and that's how it will be over throughout the presentation. What you see is you generally are able to make a connection both to the website and both to the media server. So success rate in both over 4 and 6 is fairly good. So 99% of the probes are able to achieve success rate more than 94% of the time, and which is slightly lower for 6, which is around 97%, which is still fairly good. And slightly lower success rate is not because of YouTube on the server side, but because of the probes. So sometimes they experience network connectivity issues, so they can't resolve a DNS, or they have TCP connection timeouts over 6. Okay. In situations where you can actually do connect, we started looking at, given that you measure both over 4 and 6, as a user, if you have an option, what would you prefer? And so there are 2 RFCs which are coming into the picture when making that calculation. That is RFC 6724, and which gives a preference to V6 destinations, and RFC 6555, which is happy eyeballs. So it tries to fall back to 4 in situations where you're not able to connect over 6. But we largely saw that around, in our sample of around 900 videos, in 97% of the time you will actually prefer making a connection over V6 and try to keep that connection. And so the takeaway here is that if you are dual stacked at home, you will largely be streaming videos over 6 than over 4, which is good. And once we have established that, so in terms of TCP Connect Times, or the first latency that you see after establishing a connection to a media server or to the website, what kind of latency that you experience. And what you see is around in 63% of the cases, the audio and video streams that you stream from the media server are actually slower over 6. But the difference is actually not that bad if you look at the scale of the x-axis. And in 14% of the cases, the audio video streams are 10 milliseconds slower. So I would consider this not bad. Okay, given that we have a 2-year-long data set, you can actually also look at the time series of this. And so this is median time series, and some of you might know the kind of plots I usually draw. So this is 4 minus 6, IPv4 minus IPv6, TCP Connect Time. So if you see anything on the positive scale, that shows that IPv6 is faster. And so on the y-axis, you will see that everything is on the negative scale, but the scale is fairly zoomed in. And so in terms of connections to the website, which is the top plot, you see that it's around at maximum 5 milliseconds slower when connecting to the website, and when connecting to the media server, the connection is around 0.3 milliseconds slower in median case. I would love to know what happened in the middle of the top plot where there was a drop and then it increased. Oh, again, I don't know, but if somebody from Google can tell me what happened to the website, it would be nice to know over 6. Okay, so once you have established the connection, you try to stream the video. So you try to fetch the video for 2 seconds and try to fill your buffer. And that's what we call the pre-buffering duration. So this is happening when you start making interaction with the media server and try to fetch the video for 2 seconds and fill the buffer. That is pre-buffering duration. And the entire thing, starting from when you interact with the website till the end of 2 seconds of streaming the video, is startup delay. And so startup delay is a very well-known metric in literature. So this is the amount of time it takes for the video to start playing on your screen when you stream a video in your browser. So using these 2 metrics, what kind of performance aspects do you see? So this is startup delay. Again, this is 4 minus 6. So positive is good for V6, which means faster. And what you see is 80% of the samples, which is around 6.5 million samples over the last 2.5 years, you see it is actually slower over V6. And in the median case, it's actually 100 milliseconds slower over V6, which I do not consider as good news, because 100 milliseconds is something that you can actually see as a user. And this is how it looks over the time. And so startup delay is the plot on the bottom, the pink plot. And what you see is the startup delay has been consistently been worse. That's around 100 milliseconds worse over 6 than over 4. And in terms of pre-buffering duration, which is the green plot on the top, it's around 25 milliseconds worse over 6. So if you remember the sequence diagram again, pre-buffering duration was just the interaction with the media server, and the startup delay is also including the interaction with the website. So all of a sudden, there is a higher jump from 25 milliseconds inflated latency to 100 milliseconds inflated latency when you start interacting with the website. So it's the initial interaction with the web server where you have to fetch the HTML page to identify where the media server is, which is what is increasing latency. This is something that we might have to optimize, and the interaction with the media server is not that of an issue. Okay, going forward, we keep on doing this. So we try to stream the video for a minute. And given that we do this, what you can do is you can try to capture the throughput, what you experienced over the entire 1 minute duration of running this measurement. And so this is throughput, throughput aspects of streaming the video. And what you see is 80% of the videos actually achieve lower throughput over V6. But this is not bad news, which we will see later. And in terms of time series over the last 2 years, you will also see that the throughput is consistently lower. Again, it's on the negative scale, but it seems to be improving over time. So the scale is the slope is actually increasing towards 0. Okay. Apart from latency and throughput aspects, we also looked at what happens when you experience a stall. So stalling is when you expect a packet to arrive, but it doesn't arrive and your buffer is empty. And so in that case, you rebuffer for a duration of 1 second, and then the playout resumes again. So this is stalling. And we looked at how often do you actually see stalling over 4 and 6. And so this is a CDF showing the stall rate both over 4 and 6. So red is 6 and blue is 4. And what you see is in 90% of the cases, probes do not experience much stall. It is actually less than 1%. So stalling usually doesn't happen on the internet as we see towards YouTube, as seen from these vantage points. And as a result of this, the bit rates that you can reliably stream, both over 4 and 6, are actually comparable. And what this goes to show that throughput is actually not a very reliable metric for judging performance, because even if your throughput might be lower, the bitrate that you reliably stream is still comparable, but you still experience higher latency over 6. So latency aspects are also very important, which you also saw in the previous presentation, to include when looking at performance aspects. We also looked at in situations where you do experience a stall, what is the duration of the stall that you experience, and how does it compare over 4 and 6? And what we saw was in 80% of the cases, the samples actually, probes actually experience higher stall over 6 than over 4, and it's at least 1 second longer. So if you're streaming over 6 and you experience a stall, you might be waiting 1 second longer than you would have had if you had been streaming over 4, which is not good. Okay, so what all do we take away from all of this? The first takeaway is that you might remember I showed the first plot where we showed that you actually prefer streaming videos over 6, but the performance both in terms of throughput and latency is not that good. And this is also happening because of this RFC 6555, which is using a very high timer value. So we recommend that the RFC should be updated with a lower timer value. And on V6 Ops on Tuesday, I presented some of the results, which tend to show that using a 150 millisecond, halving the timer value might actually help. And this is just a background on why a 300 millisecond timer value was used, because there were more relays, 624 and Terodo relays being used back in 2012 when this RFC was defined. And this is no longer the case with V6 deployment anymore. And as such, Happy Eyeballs also needs an update. And this is part of the charter within V6 Ops, so this is happening. So that's good news, and it might eventually work out for the best. Second recommendation is, which is fairly obvious, I think that ISP should take latency as a first-class citizen, and it's not just about throughput. And the third one is more important, where ISP should ensure that their caches, the GGC caches, are dual stacked. So I got told that this is the nodes are not dual stacked because some of the ISPs have not asked for a V6 prefix allocation from Google. And I hope if this happens, then this might be solved. Okay, so what all did we see today? We saw that clients prefer streaming YouTube videos over 6. But even though you do prefer streaming videos over 6, your performance, both in terms of latency and throughput, is bad. And when it comes to stalling of video, we do not see much stalling happening, at least from these probes. But when a stall does occur, the duration of the stall over 6 is at least 1 second higher over 6 than over 4. And this is largely happening because the GGC nodes that we hit from these probes were V4 only. And as a result of which, you might have to go further towards the CDN to fetch the video, and which increases latency. In order to encourage reproducibility of this work, we have open sourced the test. So the test is available on GitHub. So you can download the test. It's written in C. You can also run it in your own network, try to see if you actually see what we saw. And the entire data set is also available online. So you can go to that link and download the data set and play with it. That's all about from my end, and I'm happy to take questions.
Thank you.
Thank you again for this interesting presentation. And I have just one comment about the necessity to update the RFC, the happy-able RFC. Actually, there is no recommendation about the use of 300 milliseconds in that RFC. It's only one example that has been cited in the RFC, so it's up to the implementers to use whatever timers to kick off the connection. So for me, there is no update to require to that RFC at all.
That's actually correct. So that's just an example, and the 300 milliseconds is actually not recommended, but just given as an example because Chrome and Firefox were using it back then, and that's largely what people use on the internet. And so there's a trade-off here. Yeah.
Hi, Dave Olson from Sandvine. I thought it was interesting that you said the stall rates were basically the same, the bit rates were basically the same, which makes me think the user wouldn't really see any difference. And I'm wondering why that makes you conclude that latency is so important. Like, I think latency is important, but I'm not sure that that's important for videos.
Okay. That's something that we can discuss. So I have this impression that startup delay is also achievable. It's an interesting metric to look at, because if the video does not start quickly for me, it's a bad experience for me, right? And so
that wasn't latency though. That was related to, I think you said trying V4 first, or trying V6 first, and it not working in V4.
Oh no.
But anyway, I guess we can discuss this later. But I think a lot of people say, oh, if I measure latency, I'm understanding what my customers are seeing. But I think you kind of showed that's not the user's experience with watching the video. So, and then we just got to watch what we monitor. I think it is interesting that you've found this way of actually seeing the stalls and things. Anyway.
So that's an interesting point. I would like to highlight this again. Can you please highlight the PDF, please? So going back again. So startup delay, this is the one that I was talking about, and this is what I want people to take away. So this is the amount of time it takes for the video to start playing, and this is actually 100 milliseconds worse over 6. And that's why I consider latency to be important, because this is one interesting metric for user experience. And so that's why I wouldn't consider throughput and as more interesting metric, as long as you can stream the same video with the same bit rate.
Yeah, so I agree that user experience is important.
Yeah.
Michael Abrahamson. So I think when I'm looking at these graphs, and you said that things are improving over time, it would be interesting to get those those diagrams for the last 12 months of your data to see what is the current state of affairs, more than the influencing about a lot of things that seems to be going on in 2015, because that is a very if we had problems before, it's no longer a problem. I don't want it to affect the overall conclusions of what to do right now.
Would it be useful to have an online page where this is updated regularly? And
absolutely, that would be super.
Okay.
Janai Iyengar, Google. Thank you for doing this work. It's really, really interesting. I actually have a very specific question. You pointed to a dip, and you said you don't know what happened there.
Yeah.
It's uncanny. So I have a question about something that might relate to the dip. Are you confirming that the protocol that's running underneath the client is in fact TCP?
This is actually TCP, and yeah.
Okay. Okay, so one of the first graphs in my presentation, which is coming up next, is going to coincide exactly with that dip, and I don't know why.
That's we sorted them in that order. That's the most thing.
Ian Sweat, Google /YouTube. So yeah, again, thanks for doing this. This is very interesting. So when you, in terms of methodology, and maybe I just misread the slides, but did you actually have one sample set which only did V4 and one which did happy eyeballs?
Oh, so the probe is, so the test is running once over IPv6, and once the test concludes, then it is running the same thing again over V4.
Okay.
So it's at the same time, almost at the same time, and then we try to pair it. So it's not like we have a V4 data set and then V6 data set 1 month later or something like that. It's not like that.
Okay. And so the GGC nodes that don't speak V6, you just kind of ignore them from the sample set?
We have to, because we can't make a comparison between 4 and 6, and
that's totally reasonable. Okay, I mean, this is slightly surprising to me personally, but I will ask some folks and see if they have any intuition and if I can have any clarification.
Yeah, I would like to ask a clarifying question to that one. So if the closest GGC node is V4 only, you're then doing the test to a further away IPv6 enabled one, or you're just then not doing a test?
No, we are doing the test. It's just going further away.
So you're going to the closest V4 server and then to the closest V6 server.
Okay. Okay, yeah, so that probably makes a dramatic difference in the results, because as you said, there are quite a few GGC nodes that don't have V6 enabled.
Right.
Yeah. Okay.
So just to follow up, we would also like to know the expansion of GGC nodes which are dual stacked or not. So we would like to work with Google on this, perhaps combine this with RIPE Atlas or something. And so perhaps we can talk about this if you are interested.
Sure.
Yeah, Giovanni, SIDN, great work. I also have more historical question. I happen to have been during your presentation during IETF networking 2015, and you had similar measurements. I think the paper is called Who Connects Faster, and I think you measure YouTube. So my first question is are those measurements here now comparable with those? And I have the feeling that the results for V6 was far worse back in 2014-15 when you measured. And what has changed since then?
So the presentation that Giovanni is referring to was those were latency towards websites. And so this is specifically YouTube. And we have a previous paper on this at PAM in 2015, which was using dataset, a 20 days long dataset. And we would suggest people to look at this because this is covering a longer time span. So that those papers are not comparable. All right. Because they're looking at two different things.
Thank you.
Jelinkova, don't go away. One question. It would be really interesting to see two separate sets of data when nearest node is dual stack and nearest node is V4 only, because obviously, yes, it's V4 only, user experience is worse, but is there any difference if node is dual stack?
Yes, that's a very good question. So we are doing work on this, and I might not want to comment on this at this point because I have to look at the results again. But we are also looking at when the node over 4 is also when the GGC node is also not available over 4, and what is the kind of benefit that you see when you actually hit a GGC node. But also when the node is actually dual stacked. So do you actually see any difference or not? Happy to show you results privately.
Yeah, and the last comment, you're saying that operators should request IPv6 addresses from Google. That's not true.
Okay.
I say operators should provide V6 connectivity for the node, and then it will be dual stack. We currently deploying them like dual stack by default if operator has a V6 connectivity, and V4 only nodes could be converted to dual stack if operator is ready.
Okay, that's good to know. So that's my mistake.
Thank you very much. And we come to our last presentation on Quick, presented by Jana.
Hello all. Is that time anywhere?
Yeah, 25 minutes.
Thanks. Well, my name is Jana Iyengar, and I'm going to be talking about a bunch of results and data that we have now published. It's not appeared yet, but I'm happy to send you a copy of the paper if you want. Just send me an email,
or wait for a couple of weeks and it will show up on the SIGCOMM website. But this paper will appear in ACM SIGCOMM in a month. So I'm going to not go into the details of QUIC, but I'm going to start with just talking about what the history of QUIC is. How many of you here have heard about QUIC? Excellent. This should be good. So QUIC is basically a protocol for HTTP transport and runs between Google services at this point and Chrome or other mobile applications as clients. And it has reduced page load times and video latency for us and rebuffer rates, as I'll show in a moment. In general, this is sort of a TLDR slide. It reduces video rebuffers for YouTube by 15 to 18%. And Google search latency between 3.6 to 8%. It is now 35% of Google's egress traffic, which by external estimates is about 7% of total internet traffic. And the IETF QUIC working group was formed in 2016, in October last year, to standardize it. I will not be talking about IETF QUIC here. I will be talking merely about our deployment, Google's deployment of QUIC. So here's a chart that shows basically the ramp up of QUIC that's happened at Google. And we started sometime in 2014, but the numbers don't matter. At that point, it's low enough, but then we slowly ramped up QUIC. These are all driven by client Chrome, and at the time it was only Chrome that was opting to use QUIC, and we would basically we had a way to experimentally turn this on at Chrome clients. All servers were always speaking QUIC, but only some Chrome clients would opt themselves in to speak QUIC. And we ramped that up slowly over time as we found performance benefits and so on. Two things to note in this graph. I mean, you can see, of course, that at this point we've gotten up to close to 35% at the right end of this graph, but you will see that there's a big dip there right on January 2016, Vaibhav. I'm going to take away from this that when QUIC traffic goes down, TCP performs poorly. I have no fucking clue why. So we should talk more later, and this is a weird, very uncanny sort of result, but I don't see Vaibhav in the room. Anyways, oh, there you are. So it's the same time, right? Yeah, okay, yeah, we should talk. I don't know what's going on. We turned off QUIC at that time because there was we found a security bug in our code, and we rapidly turned down QUIC. And we turned back on once we shipped the fix to our clients, to Chrome. And that happened in January 2016. There's also a bit of a big bump up there near August and September 2016. Any guesses as to what that is? One guess. Somebody said mobile data. Yeah, that's exactly it. That was YouTube app starting to use QUIC. So if you had any doubt about how much data goes towards mobile, that should put it to rest. That's about half our total traffic with QUIC. Yeah.
Alex Meyer over a quick note. I think that, well, the TCP performance worsening could just be the additional load that suddenly switched over from QUIC to TCP.
It's absolutely possible. That's the only theory I have at this point. But yeah, that's the only theory that exists at this point. But if that's true, you may also he has longitudinal data, and you should see sort of over time the latency changing as QUIC increases. But I don't think that's visible in his data. But anyways, yeah, something relevant it's something clearly related to this happened there. All right. So what are we talking about? What is QUIC? I'm going to do this in very quickly. QUIC is basically a replacement of TCP, TLS, and a big chunk of HTTP2 for HTTP transport. It subsumes a whole bunch of that, and it's an encrypted transport, and that's where it sits in the IP stack. QUIC has a number of features, and I will briefly touch upon these. I will not get into the details here. The QUIC was designed to be deployable and evolvable, and by that I mean it runs on top of UDP and it is encrypted, keeping it from getting messed around by middle boxes or getting ossified by middle boxes, as I'll talk about later in this presentation. It was designed to have really low latency connection establishment. There are at least 2 presentations today that I've seen that talked about latency as being important, and that's absolutely true. There's actually dollars attached to that. Quick gives you 0 RTT connection establishment, secure connection establishment, mostly 0 RTT, which means that a client can send a client hello immediately followed by an HTTP request, an encrypted HTTP request, without waiting for a server to respond. And sometimes the client has to fall back to a 1 RTT, and in almost no cases, we do have the case for handling 2 RTTs, but that happens very rarely. Quick has multi-streaming. I will not talk about that. Quick has better loss recovery and more flexible congestion control. The loss recovery comes from Quick having better signaling to signal packets being received and better RTT estimates and so on. And finally, Quick has resilience to NAT rebinding. It runs on UDP, so we sort of need a way to make sure that NATs don't lose state mid-connection. That's about all I'm going to talk about the Quick design itself. Going on to the data. The metrics that we evaluate for this study are basically 2 broad genres, so to speak. One of them is latency, the other is rebuffer rate. Latency focuses on, well, search latency and video playback latency. Video playback latency is very similar to what Weber was talking about, which is initial load, time it takes to load the first frame of video. Search latency is an end-to-end metric. This is the total time it takes for a search query to be sent to the servers and then for the response to be received and ready to display. Video rebuffer rate has to do with, again, the total amount of rebuffer time divided by the total amount of time spent watching the video. Latency goes towards speaking to how Quick helps small connections or early small connections and connections early in the game. Video rebuffer rate talks about long-term health of the connection, typically. We focused on application-defined metrics because these are what matter to applications, and these are what drive adoption across the industry. They certainly are the things that drove adoption at Google, and I expect that's true elsewhere too. And these tend to include non-network components. If whatever change you're making makes tremendous amount of difference when you're looking at just the network part, but on an end-to-end basis, it really doesn't matter, then there's not much incentive to deploy it. And so the metrics we show are, in fact, end-to-end are quality of experience metrics that these applications define. So here's the first one. There are a lot of numbers here. Do not look at them all. I will tell you which ones to look at, and you can go read the paper for the rest. The first one is simply the mean, and the top is search, the bottom is video. There's desktop and mobile in both cases, but you can generally see that the mean latency improvements exist. They are about 8% for desktop on search and 8% for video on desktop as well. And these are pretty substantial numbers. Just as far as application metrics go, it's hard to move search latency. Search latency has a number of things in it. Network latency is just a part of it. So moving all of search latency by like 8% on desktop is a pretty big deal. And we can see here that as we plot the percentiles, most of our wins, most of that 8% or most of the mean basically comes out of the tail. And this also tells you something that's important. The tail is very important to moving application metrics that applications care about. And the tail is where a lot of the gains still exist. The tail is where we can optimize things more and actually get more gains. I'll talk about why this happens in a moment. So this is search and video latency. So as I pointed out to you, search and video latency is largely impacted by things that happen up front. And the reduction, the 0 RTT handshake that I mentioned earlier is kind of critical to this reduction, to this improvement. And this is a micro benchmark that just measures handshake latency. Do not read the text, I'm sorry, that got left in, I meant to remove it. This is simply showing handshake latency measured for TCP versus QUIC. Forget the subscript of G. Those are, again, you can read the paper for more details. Those are experiment groups are called those. But the folks who are using TCP end up having that yellow line. As your RTT increases, the x-axis has increasing round-trip time to clients. This is the minimum round-trip time measured to those users. And the handshake latency goes up. This is expected. There are about three round-trip times for establishing a TLS connection. And so if you have a certain round-trip time, the handshake latency is simply usually 3 times that round-trip time. And that's what we observe in the wild. With QUIC, you can see that it's almost flat and near 0. And that's because 88% of our connections on desktop get 0 RTT connectivity. That's a pretty large number, and we are able to achieve that. And even when we don't get 0 RTT, the thin blue line in the middle shows you what the remaining 12% of our users experience, and that's still 1 RTT. So you can easily see the savings here are quite substantial. So 0 RTT saves a lot, and it actually contributes quite a bit to search and video latencies. The second metric that I mentioned, the second genre of metrics, is video rebuffer rate. These numbers are different, and the numbers look different, so I'll explain them. The mean, again, shows these are reductions in rebuffer rate. Fewer rebuffers are better, and we get about an 18% reduction on desktop with QUIC in rebuffer rates, and 15.3% reduction on mobile at the mean. As it turns out, when you look at the percentile data, when you lay this out, up to 93 percentile, up to the 93rd percentile, videos have basically no rebuffers. So all of these wins are coming from the tail. So QUIC can't improve anything. That's what the asterisk is there mean. QUIC cannot improve anything up to the 93rd percentile in rebuffer rate, because on TCP even, these playbacks have no rebuffers. And as these playbacks go into the tail, as the rebuffers go into the tail, QUIC pulls the mass in. The reduction here says, at the 93rd percentile, this says QUIC gives you 100% reductions in rebuffers on desktop. What that means is that TCP experienced non-zero rebuffers and QUIC experienced 0 rebuffers at the 93rd percentile of rebuffers. So that's how you see this. At 94, QUIC reduces rebuffers by 70.4%. What that means is that you're starting to see rebuffers in QUIC at this point. So this sort of pulls the tail in and again, moves the mean quite significantly. So what are the causes for the rebuffer rate improving? The first thing I'll point out is that all of these metrics, not just the rebuffer rate, all the metrics, the latency metrics and the rebuffer rate metrics, improve more. QUIC has greater improvements as the round-trip time to the user increases. Now this should be obvious for the latency metrics, because as the round-trip time increases, there's more handshake latency, and therefore QUIC improvements are higher. That's fine, but that happens to be true for rebuffer rate as well. And now remember, rebuffer rate has more to do with long-term connection health, right? Not just initial startup. So it has much more to do with long-term connection health. But even there, we see that the metrics that QUIC actually offers more or improves more as the round-trip time to the client increases. And this has to do with the fact that network loss rate increases with round-trip time. This is a graph that shows TCP retransmit rates plotted against minimum round-trip time to the user. And this basically, TCP retransmission rate here is used as a proxy for network congestion or loss in general. And you can see roughly that the trend, there's definitely very strong correlation here. The retransmit rates go up as the RTT to the client goes up. This tends to be true because these are clients who are either in places which have poorer connectivity, and therefore, or Google doesn't have a node sitting there, a GGC node sitting there, and there are lots of reasons why this is true, but we find that delay is correlated with network quality. RTT is correlated with network quality. So what this means, or at least what this tells us, is that as loss rate increases, as RTT increases, Quick has more improvements to offer. The Quick improvements show up more. This is borne out in, sorry. Yes, I will get to this point in a moment. The second reason we see improvements is because we found that about 4.6% of all TCP connections were limited by the advertised receive window from the client. This is where the server's congestion window basically hit the receive window and therefore could not grow any further. There's a CDF of the distribution of this. You see that there's a good chunk of them that are limited by a 64K receive window. But that's what that is. Basically, these are things that are ecosystem problems where a server can't change anything. This is client advertised receive windows, and it's kind of hard to change this. Quick advertise is a large receive window, of course, and so this problem doesn't exist in Quick. So between loss recovery and receive window limitations, Quick seems to have a leg up over TCP. Yes, 5 minutes. So the loss recovery thing plays in here. We find that most of our improvements globally come from countries where connectivity is poor. South Korea, for instance, barely sees any improvements. India, on the other hand, sees substantial improvements with Quick. So this is just to say that Quick is not a protocol that's particularly useful for really well-connected networks. You're not reducing latencies from small latencies. This actually has pretty big impact for users who already have poor connectivity. And that's one of the benefits that we see for having Quick.
Jana, can I quickly ask which congestion control does this data use?
Good question. So we use cubic for this data, but it's 2-connection cubic in the congestion avoidance phase. It does 2-connection emulation. And that's because YouTube itself uses 2 separate connections. It's not apples to apples, but that's what we have. So I have only a couple of minutes. Instead of talking about these things, I'll just put these slides up. You can look at them. I'm happy to take questions.
Hey, Andrew Dogan on Nokia. I have a quick question to you guys because now Quick is by default enabled in Chrome.
Yes.
And we have to say, so I live in a part of the world, like in Singapore, where you're actually not helping. You're making it slower. Because of, our access is 1 gig, 2 gig. Those are the options we have. In South Korea, you have 500 meg, so for a slow connection. And what we're seeing is some of the infrastructure is actually blocking Quick for various security reasons. And then that introduces delay. So Quick actually doesn't help, but in those geolocations, and actually makes things worse because of some infrastructure settings. You go somewhere, you connect to a hotel, you're most likely gonna be filtered. In Asia, in various Asian countries. So I was wondering if you guys looking at making it more geo aware, so we enable it, because no questions, enabling it here, enabling it in India, countries like this, great help, but enabling it in countries which have good connectivity, we actually contributing to a problem.
So the first thing is that it shouldn't hurt. And if it is hurting, then I'd like to talk to you and find out why. Second, if operators are blocking it, that's fine. Chrome will end up using TCP. That's what this slide says. We are fine with complete blockage.
But that handshake is happening. Yeah. So
blocking
drops and then you flip. So then.
So let me finish.
So that's the delay. That's what I'm saying. So that's the delay that's happening in certain places. That's what I was saying. I'm not saying it stops working, but because in those jurisdictions that have a good connectivity, as you noticed, there is hardly any, if at all, improvement. But then you're introducing this.
So there's hardly any improvement in terms of the actual performance as measured by YouTube or by Google search. But I think there's a general value in being able to deploy Quick, because we expect that this is going to be more feature-rich going into the future. It's an encrypted transport. That by itself is an additional value that's not measured in these graphs. So I would like to see Quick deployed there as well. and I'd like to talk to you about exactly what the delays are. We are working on situations where we do have situations where middle boxes will actually drop traffic after the handshake, and that causes us heartburn, and we are working on detecting that and repairing those things.
Okay. Thanks.
Hi, Colin Perkins. Are you able to break down the performance results based on the TCP version running at the receiver? So is it that you're always winning out against old versions of TCP, for example, and not against new versions? Or do you not have the data to tell?
Not that data, not the high-level metrics data. That's really hard to do a join between, but there's some other data that we are taking into. Those are more micro benchmarky, but yeah. So I can tell you that from the Chrome user base, most of our desktop clients are Windows, but the question that you're asking is which version of Windows.
Yeah.
I think I could get some data about the Chrome distribution. Maybe that'll help.
Maybe. Yeah. Thank you.
Sure.
So it's just noon now, so unfortunately we're out of time, but Michael, you can ask your question, and it's up to Jana if he wants to hang in and take more.
Oh, sure. I'm fine.
Michael Abrahamson, are you saying packet size too large? Are you doing packet level path into discovery?
We're not doing packet level path increase here. This slide in fact shows we did a bunch of experiments. We found what packet sizes work for most of our clients, and that's what we ended up using. We fixed it at 1350 bytes.
1350. Okay.
Yeah.
Marcus Hille. The mobile results, can you differentiate if it's the clients are connected over Wi-Fi or cellular access as well?
We don't do it in this data. Again, I don't know how far we can actually tie in the application metrics to that level of detail. I'll have to look into it, but we don't have that data right now.
Okay.
I guess that's about it. Please do read the paper. There's a very fun story about middle box ossification that we already experienced. If you believe it, if you can, Quick is already ossified. There are middle boxes. There is one particular middle box who shall remain nameless at the mic, but I'll tell you when you ask me offline, who took the one byte that was visible and decided to put it into their firewalls as a way to detect Quick. And this was the flags byte. And that obviously caused breakages. But read the paper. Thank you.
Thank you. Thank you, everybody, for contributing. And if you have data, maybe consider to send it on the mailing list or to us early, or like you want to present something, because we have quite a lot of requests these days, which is great. But the earlier you let us know, the better. Thank you very much. See you next time. Thank you. Yeah. If you haven't signed the blue sheet yet, come to the front. Thank you so much. You did all the work this time.